title of my talk is Phoenix Lander Dishes Dirt on Mars, Discoveries from this long-awaited mission. And the title, Dishes Dirt, because one of the main focuses of this mission is actually digging into the Martian soil to look at the ice and the geography of the soil. So let's go ahead and give you quick. I know that many of you here are not Mars people, and since it's a general public talk, I thought I'd give a very quick overview on just some of the basics of Mars to get everyone kind of oriented to what Mars is like and just the overall conditions of this lander. So Mars at a glance, Mars is about half the size of Earth. 1 year on Mars is about 687 days. So it's almost 2 Earth years for 1 Mars year. 1 day is about the same on Mars as it is here on Earth. It's about 24 hours and about 40 minutes. So initially when this lander first landed, most of the Phoenix team was working on Mars. As days go by, you start cycling through the days. So I know a lot of them were pretty exhausted by the time they actually went back to Earth days. The poles on Mars are tilted very similar to the Earth, so about 25 degrees. So Mars is going to go through seasons very similar to what the Earth sees. The atmosphere is 95% carbon dioxide, so not very conducive to life as we know it right now. The pressure, the atmospheric pressure at the surface is about 1/100th of that of the Earth. So there is an atmosphere on Mars, but it is very much thinner than what we used to here. We can see surface winds up to 80 miles per hour. At the Phoenix side, this will be less, on the order of about 40 miles per hour. So you do see dust devils on the surface and things like that. Average temperature is -64 degrees Fahrenheit. So Mars is a frozen planet. You do see a range from -199 to 80 degrees Fahrenheit, and that 80 degrees is an extreme at the equator during the closest approach of Mars to the Earth. To the sun. There are 2 moons, Phobos and Deimos, and on landing day at Phoenix, the distance from Earth to Mars was 171 million miles. So the radio signal from Mars to the Earth took about 15 minutes, just for that one-way traffic. So that gives you an idea of the enormity of how impressive this mission actually is. Here's a view of the topography of Mars. This is an elevation map, so white is high, blues are low. And there's a couple of major features you see on the surface. You have a huge volcanic complex here. We do see one of the largest volcanoes in the solar system on the surface. A little dim for the laser pointer. You have Hellas Basin and Utopia Basin, a couple of the largest basins in the solar system as well. The surface of Mars is pretty ancient, as you can see by all the craters on the surface. Most of the surface, what you see, is on the order of like 3 billion years old. The northern lowlands is, underneath it's about the same age, but it's been resurfaced by a lot of material, so you see fewer craters in the northern lowlands than you do in the southern highlands. I have labeled on this is all of the landers or rovers we have on the surface. Back in the 70s, we had 2 landers, Viking 1 and Viking 2, in 1976. I think Viking 1 was one of the longest lasting landers on the surface. I think it lasted, I'm probably going to get this wrong, I think it's close to 6 years. Viking 2 only lasted only a small fraction of that. And they were landers, they didn't go anywhere. We had Pathfinder lander in 1997, and then in 2004, we had Opportunity and Spirit, where the Mir rovers landed on the surface. And they are still operating today. They're a little geriatric is what they call them, because they each have little things like one wheel doesn't work on one of the rovers and things like that, but they're still going strong. And Phoenix is the mission we're going to talk about today. Lander location. Now Phoenix did land very close to the northern pole. As you can see here, it's about 68 degrees north. Now if you think about Earth and want to do a national comparison about where that would be on Earth, we're looking at pretty much northern Alaska. So that kind of gives you an idea of what type of terrain we'll be looking at. It's mostly going to be permafrost and ice-related terrain. The landing site, here's just a view of kind of a geologic map of where we actually landed. The colors are corresponding to different types of terrain in the region. There's a crater here, a smaller crater there, One of the reasons why we landed here is because there are very few rocks or hazards for the lander, so it's fairly safe for the lander overall. And we also are on part of the ejector blanket, which is this yellow. So part of the idea here is we can actually get a glimpse into, when the crater formed, it kind of threw up material from depth. So that gives us a look at what the actual history of the region is like by looking at the material, if we can land on the ejector blanket. So here's a glimpse of a view of part of the landing ellipse from high-rise. The Martian Reconnaissance Orbiter has a camera aboard that's called high-rise, and the resolution of this camera is pretty remarkable. We have pixel size of this camera will take about 25 to 30 centimeters per pixel. So we can resolve features on the surface that are about a meter or about a yard wide. So that's a pretty incredible resolution. You can actually see that little boulder there is probably about a couple of meters wide, probably about the size of this table, just to know this portion of the table. So it's been an invaluable tool for actually looking at the landing site to figure out where is safe to land. You don't want to have too many large boulders, because you land on it, obviously you're going to run into issues with tipping the lander over. Here is that same crater we saw on the previous slide, and this is the landing ellipse. And all of these squares, or all these rectangles you see here, are all high-rise images. So in the year and a half leading up to this mission, we pretty much blanketed this entire site with high-rise images to really get a good look of what are we going to see when we land. And here's the red stars where we actually landed, so fairly close to the center of the predicted ellipse. So that's pretty impressive. Now, as you can see from this, most of this surface is covered by polygons. So what are the polygons? Well, polygons usually occur on the surface due to thermal contractions. When you have a surface and it heats up and cools down, it kind of expands and contracts. Well, that expansion and contraction is going to cause cracking. And that cracking, if it's a humid environment, or if you have liquid water there, you can have, during the cold months, it'll contract and have a crack open up. You can have water or fluids that get down to that crack and cause an ice wedge, which is what you see in this diagram here. A crack forms, and each season you get more and more ice going into that crack, and the crack just slowly opens up. Now, in a drier environment, you're not going to have ice getting down into those cracks. You're going to have sand getting into those cracks. So that's more like this scenario here. And this is a picture from Antarctica in the Dry Valley. This kind of shows what this type of polygon would look like if you kind of cleared off the loose topsoil and get down to the frozen soil below that. You can kind of see this is the crack where the wedge occurs, and you do get sand and debris falling into that crack season to season. This image here, it's kind of hard to tell, but this is an example of an ice wedge. You can see here is a cross section of it. Here's the actual ice wedge, and you can see little laminated, I think I just lost my point, there it is. You can see little laminations of ice that represent the seasons. Here's an example of what this looks like from the surface. Now on Mars, it's a fairly dry environment. So we don't expect to see ice wedges. It'll most likely be sand wedges on the Mars surface. Here's just an example of what these polygons look like. These are just random images taken from this region. As you can see, it's fairly uniform. The polygons are on average about 5 meters wide. So as you can see from these. We do have boulders on the surface. Sometimes the boulders try to collect into rubble piles, which are a little mysterious. We're not quite sure how the rubble piles form yet. So that's a fairly interesting subject. So in the Phoenix region, we kind of done a survey of what these polygons, the sizes and the morphology of these polygons. On average, about 4.6 meters. They're ubiquitous, and they pretty much are everywhere. I mean, you just take an image at random and look at it, and you're going to see pretty much the same thing. Which is kind of, it's good for the lander because this is a lander, it's not a rover. So if we're going to land, we want to make sure we're going to land in a region that's representative of this entire region. So that's good for the lander. The polygons are consistent with having shallow ground ice. And they're consistent with these thermal contraction polygons as I described. And one important thing to note is these do not require freeze thaw. So the current atmosphere on Mars is frozen. and they're more consistent with ice-rich soil than pure ice. So what you have here is you have a dry layer of soil, and below that you'll have an ice-cemented soil that has these cracks forming in it. We also see some larger scale polygons, and some rubble piles are also common. We did avoid a lot of these rubble piles just for risk factor. So just from seeing these polygons, we know that there's going to be ice here. We can also detect that from the orbiter. There's an orbiter, Odyssey, that has a gamma ray spectrometer that detects hydrogen in the surface. And from this, we know that we can predict the weight percent of water. And about 68, which is about right here, is where the lander is. We would expect to see ice at this location. So here's just an estimate of, okay, we have ice here, how deep is the ice? Well, we can kind of guesstimate at how deep the ice is from the size of the polygons. We can also guesstimate how deep the ice is from the amount of water predicted from the Odyssey spacecraft, as well as a few other methods of predicting the ice table depth. Here's just a summary of some different methods of trying to predict how deep is this ice going to be. So if we're going to send a lander there, we want to make sure that we can actually get down to this ice. And on average, they're estimating anywhere from 2 to 6 centimeters. So this kind of leads into the NASA strategy of follow the water. Water is a major component of life. It plays a large role in the climate, geology, and it's important for humans as well. So NASA strategies follow the water. Most of the missions currently, like the rovers, are all on the search for, is there liquid water, is there life? So this ties into this quite well, actually. From the ashes, Phoenix is named Phoenix for a reason. It is actually an accumulation of a few different spacecrafts. In 1999, we had a Mars polar lander that was lost during entry. Not quite sure what happened to the Mars polar lander. They think that one thing that may have happened was it deploys legs to land on. They think the vibration from that deployment could have shaken the spacecraft enough that it turned off the thrusters. So instead of dropping from a nice low altitude, it dropped from about 40 meters up, I believe. So that's one guesstimate, but we're not quite sure what happened to it. And we've been looking at high-res images to try to figure out where this lander went, and we haven't found it yet. So we're still looking. Hopefully, we have hope that we'll be able to see this lander sometime. But from this polar lander, we have 2 instruments that have been pulled over onto this the Phoenix lander. And also from the Mars Surveyor lander of 2001. This mission was actually a canceled mission. The lander was built. It's built by Lockheed Martin down in Denver, and it was in a clean room, and it never actually launched. And from this mission, we pulled over the robotic arm, the robotic arm camera, and another instrument called NECA, which I'll discuss here in a second. But this lander was actually in a clean room, and it had some parts scavenged off it for other missions. I know that they used a part for the Mars Reconnaissance Orbiter, and they also pulled off some parts for the MER rovers. So it's in a clean room. It's been kind of pulled apart bit by bit, but they came back to it because it was overall a complete mission. It was an inexpensive mission because everything's pretty much done. Even the instruments, they took them and they repurposed them a little bit and improved on what they had. So that made this a very very doable mission. So here's the final, what it ended up being. You have weather and climate. You have several instruments that are designed to give you more information about the weather and climate, like the LiDAR. You have a surface area imager. You have meteorological instruments, as well as mineralogy and chemistry. You have a TEGA, and I'll discuss these instruments one at a time. Just to give you a quick overview about what they are and what they can do. And you also have a robotic arm camera and a robotic arm. Just to give you an idea of size, this instrument deck here is about 1.5 meters. And the span from solar panel to solar panel from tip to tip is about almost 8 feet. So that gives you an idea of size. I think height is, the instrument deck is about this tall, and the top of this meteorological station is, again, about 8 feet. So I mentioned the TEGA instrument, which is a thermal emission gas analyzer. These are basically high temperature ovens and combined with mass spectrometer. So they have 8 ovens, and these ovens are really small, about the size of an ink cartridge on a pen. And they can take samples up to temperatures of 1800 degrees Fahrenheit. This is what it looks like. They're these little ovens. Each one of these little flaps is an oven. You can open up the door and you can dump in a soil sample. And step by step, it'll slowly heat up this sample of soil to see what gases are released from the soil. And from knowing what gases are released at what temperatures, you get at what is the mineralogy of the soil and what volatiles do we have in the soil. And this is an example of the first scoop. They're a little over-eager with that first dump of soil. They dumped a little bit too much on. So yeah, they had to deal with that. Another instrument is microscopy, electrochemistry, and conductivity analyzer, or MECA. There are several components or other smaller instruments as part of this package. The overall goal of this is just to characterize the soil. So you have the white chemistry lab, and there are 4 of these. And here's an example of what chemistry lab is. You can put a soil sample into this chamber of water, essentially, and you can also put in some acidic and things like that. And there are probes that can detect what anions or cations are released from this sample. You can determine the pH, and you can also determine abundance of minerals such as magnesium, sodium cations, or chloride, bromide, sulfate anions, things of that nature. This also has microscopes to examine soil grains and ice samples to help determine the origin and mineralogy of the soil and the ice. There's an optical microscope with a resolution of about 4 microns per pixel. And there's also an atomic force microscope, a resolution of about 10 nanometers. So pretty impressive overall. And here's an example of that instrument. This is a wheel that you put little samples on, and that wheel can rotate. And this is part of the actual microscopes here. And you can also shine different color filtered lights on it to get information that way as well. It also has TEGA, which is a thermal and electrical conductivity probe, which you can see here on the robotic arm, these probes here. And you can get this into the soil, and this can determine what is the temperature of the soil, or the air for that matter. What are the thermal properties of the soil? How does heat get transferred to the soil? And it also can determine the electrical conductivity of the soil, which gets at what is the moisture content of the soil. We also have a meteorological station, or MET, and it was kind of fun because at the early days of the mission, they actually gave daily weather reports. And this is an example of the most recent weather report they've actually given out. We're currently on Sol 132, which is we won 132nd Mars day on the surface of Mars. And on Sol 112, which I think was beginning of September, the maximum temperature was negative 31 degrees Fahrenheit, and the minimum temperature was negative 130 degrees Fahrenheit, and we saw some dust devils that day. So this is on the public website. It's kind of a fun thing to look at. Here's an example of, or here's what the MET mass looks like. And each of these little football goals are actually temperature sensors. And you can also tell what's the pressure, what's the wind velocity, and things of that nature. The robotic arm is a major component of the lander. It's what delivers the samples to all the different instruments, as well as it allows us to dig down to the ice to determine where is the ice. The robotic arm is just under 8 feet, so it has a pretty good reach. It has a scoop on the end, and that's 10 centimeters wide. And there's a little rasp on the scoop to help, if you encounter a hard substance, you can use that rasp to kind of help kick some of the hard stuff into the scoop for a sample. Here is the TECP probe. And there's also a robotic arm camera, which you see right here. On the main science deck, we also have a surface stereo imager. It's multispectral. There are 12 wavelengths that we can image. It's optical through the infrared. So we also get some great analysis and DEMs because we do have 2 eyes. So we do get some depth information from this. Here's a picture of the stereo surface imager, actually taking a picture of the robotic arm camera taking a picture of the stereo imager. So this is just kind of to show you, this is what that looks like. This is the filters that you can rotate in and out. These are 5 to 12 filters for the camera. Now that we've talked about what's on the lander, let's actually get to the launch, landing, and what we've found while we've been there. It launched on a ULA Delta II rocket from Cape Canaveral on August 4, 2007, and actually launched fairly early in the morning. And one of the amazing things is, since they lost the Mars Polar Lander, they were trying to do everything they could to make sure that they could get a safe landing, or at least know what happens to the lander if something goes wrong. So one thing we tried, and I actually didn't think this was going to work. They had the high-rise orbiter taking pictures, and they actually timed it so that the Mars Reconnaissance Orbiter was overhead at the time that the lander was going through the atmosphere. We took a picture of it. Now the odds of actually getting this picture, I thought were pretty slim, but I'm always amazed by the crew at JPL. They were pretty amazing. So we actually did get an image of the lander as it was going through the atmosphere. Now this lander is a pretty good size, so when it hits the atmosphere, initially you have a parachute that pops out, and then shortly after that you have a heat shield on it that jettisons away. And then as it's closer and closer to surface, you have thrusters that will kick on and gently land the lander at about 5 miles per hour. So that at this stage, the parachute has been deployed. Here's the lander. You can see that's a parachute. And this is what the parachute looks like from an Earth test. And if you look close enough, you can actually see the gap here. And you can actually see some of these colored stripes on it. And you can actually see some of the lines leading from the parachute to the actual lander. And I believe that there's also in this image, somewhere in this region, you can actually see the heat shield that has been jettisoned off of it. It appears that the Phoenix is actually going to land inside of this crater. In actuality, we landed about, forgetting my actual distances, about 15 kilometers from it. So just from the position of the orbiter at this time, it looks like it's going to land in it. So this is a view from high rise after we landed. So again, polygons are just as we expected to see. Here is the Phoenix lander, and you can see the solar panels are deployed. And it was actually designed so that it would land facing north, so that you get most of the working area in shadow. So it was, it landed, I think, almost 5 degrees off of north. So it's a pretty incredible landing. We also can see the heat shield, where that landed here. There's a heat shield, and there's where it bounced on the surface before it came to rest. We can also see the back shell and parachute. And again, you can make out even the stripes of the parachute if you zoom in and look a little closer. Here's again that same image, and we actually have a before image, because I mentioned before we kind of blanketed this area with high-rise images even before we landed. So we kind of go back and forth and to know, we landed here, where did we land in respect to the polygons? Because the lander is actually covering up some of what we can see. So you kind of go back and forth and get a good image of what is a train like without the lander there. And these are some of the first pictures from Phoenix on the first day of landing. Well, the first thing it did, first a couple of weeks, the engineers were in charge, so of course they take pictures of their feet, you know, with the solar panels and things like that. So this is one of the first images. It's of the footpad. And this is one of the first images from looking out in the distance. And you can't see the topography of the polygons. And again, this is the engineers who are in charge. They look underneath to make sure everything's fine underneath. That's the only chance they have to look at this foot. And one of the amazing things is that this is the first indication that, yes, we found ice. Because the thrusters cleared off the top layer, the top 5-6 centimeters of soil. And what we are looking at here, this flat surface is the ice-emitted soil. So this is the first, thumbs up moment for everyone, the fact that, all of our predictions are pretty close to accurate here. Here's a close-up of the ice exposed by the thrusters, and you do see some topography in the ice and some cracks in the ice. I think that this whole pit right here is where this rock was cemented in. You kind of see where it skipped off from the force of the thrusters. And this is one of the first samples we took with the robotic arm. Again, just showing the overall terrain. We do have a little bit of dust collected on top of the solar panels. Also, that could be from thrusters that kicked up a little bit of dust that landed on top of it. We do have a stereo imager, so we can get digital elevation maps of the surface. So the overall topography of the landing site is about 20 centimeters of relief. And we did land in the middle of polygons, so here you have polygons. You can actually trace out the edge of the polygons in this region. Now the overall digging area, I should mention the naming schemes. I don't know why or who or how. I think it's Peter Smith, who's the science principal investigator of the mission. For each lander, they usually have a naming scheme, and the naming scheme for Phoenix is fairy tales. So, and they actually have a list of approved fairy tales. You can't use ones that are copyrighted. So I don't think you can use the Seven Dwarfs are off the list. So, so there's quite a bit of fun when we actually go through the list of what these features are called. The first trench they dug is Dodo Goldilocks, and Snow White was the next one that they dug. And the yellow boxes are trenches that have since been dug since this image was made. You have a trench right here that's called Covered, the trench here that's called Neverland. You have a few more that have been dug in the last week as well, which I'll talk about here in a minute. And of course, we dug down, and the robotic arm digs down until it hits hard substrate. And then it'll kind of take several passes and then kind of clean out the hard substrate to actually get a nice, clear, smooth surface. And this is what we see when we do that. I should mention that these images are stretched. Like you see white at the bottom. This white is, in reality, if you're looking at it, it is still a red color. Just the images have been stretched to make them look white. So what you are seeing here is the ice table. And actually people look at this, okay, how do we know this is ice? This could be just hard salt or something. And one thing that they looked at is on Sol 20, or the 20th Mars day, they looked at this trench and saw these little chunks that were dug up with the robotic arm. They went to the same spot 4 days later, and these chunks were gone. And so here's what they were, and here's the exact same spot 4 days later. And they have disappeared. So that kind of leans toward, okay, this most likely isn't going to be salt. It goes away, it's most likely ice that has submarinated away. So all this is again, supporting the predictions. Currently where we're at is we're doing more digging. One thing that we have done is we have this Neverland trench that was dug, and there's a rock here that's called headless. And one idea is if you have a rock on the surface, rocks are heat sinks. So this rock is going to heat up pretty quickly. So if you have hot rocks sitting on ice cemented soil, that ice is going to retreat. So one thing we can predict is that if you have a uniform ice table, if you have a rock sitting here, the ice table is going to dip down underneath that rock. And some people here at the University of Colorado, Hannah Sizemore is one who's actually leading this, modeling for this. We can actually do models to determine how far will this ice recede. And so here we're going to actually try to test that. Because we moved this rock headless out of the way, it's now sitting about right here. And this trench, which is called Pet Donkey, we're actually attempting to dig down to the ice table to determine, is this ice table actually responding to where that rock was. I think on Wednesday is when we're actually going to go in and clean this up a little bit more. We haven't hit the ice table yet on this trench, so we don't have the results of this just yet. There's also another trench that's being dug. I think it was cleaned up today, so we'll actually look at those images tomorrow. It's about right here. And one thing we do want to do is we want to know, how does the ice table vary as we move from one region to another? Because you have these large-scale polygons, and you do expect the depth to the ice table to vary as you move from one location to another with respect to these polygons and the troughs. You expect that the troughs may be a little bit deeper, the same with the Polygon, the ice will be a little shallower. So we're trying to kind of excavate different regions to determine how does the ice table depth vary from region to region. Now, digging is a large part of the mission, but we also have the other instruments I mentioned, like the TEGA and the WICL is what we call it, it's the Wet Chemistry Lab. So what have they really found? A lot of this type of work is going to take a while to really sort through all the data that they've really gotten. Some of the preliminary results from the thermal emission gas analyzer, they have determined CO2 and water, and H2O. They've run these to temperatures of 200 to 1,000 degrees Celsius. And one fairly recent result is they detected calcium carbonate with this. Now this calcium carbonate is actually more commonly known as chalk. And it is exciting because usually to form calcium carbonate, you need liquid water. So everything we've been talking about so far is frozen. You're dealing with hard ice, been frozen for a long time. So any indication we had liquid water on the surface is actually a major find. So they are looking at that with the idea that there could have been liquid water on the surface. The WICL, the Wet Chemistry Lab, it's taking samples from the surface and the subsurface. So they've taken samples from a variety of horizons in the soil. The soils are alkaline, and they detected small amounts of sulfates, chlorine, potassium. They also see that there are some gradients from the surface to the top of the ice table. So that's going to be an interesting analysis there. Back in, I think it's probably July, they also detected perchlorate salts. And these are highly oxidizing. What chlorate is just a chlorine surrounded by 4 oxygens. It can occur naturally on the surface of Earth. It can also be found in, I think, rocket fuel and fireworks. Now, you see here, it can be found in rocket fuel. This is not going to be contamination from the thrusters, because the thrusters that Phoenix actually used for, I'm forgetting what they were, but it wasn't a perchlorate hydrazine. Is what they actually use for the thrusters. So as far as why perchlorates are highly oxidizing, it doesn't mean you can't have life. It doesn't mean, yes, there is life. So there needs to be more analysis to see how does this really relate to life on Mars. And right now, it's still a big question mark. As far as the microscopes, the lava particles are below the resolution of the optical microscope. There are a variety of different colors of sand particles. Just that gives you some information about what is the actual makeup of the soil. And they're also, they detected possible phyllosilicates, which are clay. And again, this is kind of exciting because this also indicates that we could have liquid water. Because on Earth, clays and phyllosilicates do need liquid water to form. And here's their evidence for that. We have a Mars particle here, and this is an Earth particle of phyllosilicates. So very similar in their overall structure. Weather and climate at 68 degrees north. The average for the first 2 months that we were on the surface was about negative 22 degrees Fahrenheit. The average maximum, the average minimum was about negative 110. So still extremely cold. It's like a cold day in Antarctica. And winds, mostly southerly during the day, easterly at night, average wind speed about 8.9 miles per hour. The pressure is steadily decreasing from 8.5 to 7.5 at this time. And it continues to decrease as the seasons change. Visibility is usually clear with a little bit of haze in the atmosphere. Now, as we're changing from summertime to closer to northern wintertime, we did see snow with the LiDAR. This LiDAR measurement was taken on Sol 99, which is, I think, September 4th, if I remember correctly. And these are the clouds. What you're seeing here is a little bit of snow starting to continue in the atmosphere, and as it's falling, there are stronger winds at this level than at the 4 kilometers. So it's starting to actually get entrained by the wind. Now this snow has never actually reached the ground that we've seen anyway. So you do have snow in the atmosphere, but it is pretty much dissipating before it hits the surface. We do see dust devils on the surface. We didn't see any earlier in the mission during summer, but as we're getting closer to fall, we're starting to see more and more dust devils appear. Here's one here. There are movies of these dust devils moving across the surface, and I didn't even want to try to get them to work on a PowerPoint. I'm not that clever. but they're kind of fun to watch the movies. Now, as these devils get closer to the lander, we do detect dips in the pressure as they pass by. Now, these dust devils are mainly whirlwinds that occur. You have the sun that heats the surface. The surface heats the layer of air right above it. And this layer of warm air wants to rise. So that's what causes the dust devils to form, is this rising air and trains a little bit of dust from the surface. The wind speeds are about 11 miles per hour. And the whirlwinds are getting stronger due to decreases in differences between daytime and nighttime temperatures. And so that's one of the main reasons why we're seeing more of them as we're getting closer to the fall and winter seasons. One thing to mention is, since we are so far north and the tilt of Mars is very similar to the Earth, so as we see in Earth, as you get closer to the North Pole, there are seasons where the sun never sets. That's the same thing here on Mars. Here's a time-lapse image of the sun showing that we get close to the horizon, but we never quite set. So this is good news for the solar panels. But this also means that in the wintertime, the sun sets and it doesn't come up. So this is pretty much a one-shot deal as far as this mission goes. We do have a set end to this mission, unlike the rovers, which have been going for 4 years plus. Because we don't have power, but that's pretty much going to be the end of it. Here's an overall map of what the sun is. This is the day, and this is the hours of sunlight per sol. And right now, I think we're about right here as far as we have about 4 hours of darkness now, I believe. And solar conjunction, right now we're getting close to the point where you have the sun, you have the Earth on one side, and Mars is going to be pretty much opposite us. So come November, the communication between us and Mars is going to be extremely limited. I know that the Mars reconnaissance orbiter is going to stop imaging with the high-res imager, and most of the other instruments are also going to shut down for most of, I think, mid-November to mid-December. We're not going to be getting any data from most of these orbiters. I think we'll do periodic, pings to things to make sure it's still there, that there's not going to be a lot of actual science going on. Okay, so you have solar conjunction. We come out of solar conjunction. At that point, we're getting close enough to winter time that most of the surface here is going to be coated by water frost and then a layer of CO2 frost. So that's pretty much going to be the end of Phoenix. We are starting to see frost on the surface during night. I think these images are taken about 3 a.m. As you can see, there's frost coating the surface here. And this is what they call a telltale. This is about 4 centimeters tall, just a couple inches. And this is their wind gauge. This telltale just kind of sways in the breeze, and they monitor the movement of it to actually determine what is the wind speed. And we are seeing frost collect on the telltale and the spot board. I'm not sure what that's called. We have not seen any frost at the daytime yet. I don't think we'll see any frost on this surface during the day for another month or so, at least. Current status, overall, Phoenix is happy and healthy. We're still digging ditches and collecting samples. We are having less sunlight shining on the solar panels, so we are on more of a constrained by power as far as what we can do, but we're still operating and doing good. The polar hood is moving in. This is a high-res image of the surface. So if you look closely, you can see some polygons down there. All this hazy stuff are clouds that are moving in. As we're getting closer to wintertime in the north, you have a lot of water in the atmosphere that's starting to condense on the North Pole cap. So this water in the atmosphere is creating a haze over most of the landing site. So this haze will just continue to get worse until it really obscures the view of the surface of Mars for most of the wintertime. Overall, there is not giving enough energy to run all the heaters past October 24th, I think was the most recent predict I've seen. So at that point, they're actually going to turn off the heaters to the robotic arm. So come October 24th, the robotic arm is no longer going to be working. And shortly thereafter, they're going to turn off the heaters to all the other instruments as well. But they expect after you turn off all the heaters to everything, the batteries really don't like the cold, and the charge in the batteries may last less than 10 days before the batteries are completely drained. Phoenix does have orders to phone home next spring. If you have enough sunlight on the solar panels to actually charge the batteries up a little bit, once they reach a certain amount of charge, Phoenix is supposed to send out a signal saying, hey, I'm alive. And we'll see if that actually happens or not. There may not be enough, the battery may not be able to keep enough charge to actually perform that task, but we're going to give it a shot. I mentioned that you can have a lot of frost on the ground. This is actually what it looked like last summer as we're getting into spring. This is what the surface in the Phoenix Landing region looks like with the frost on the ground. You can still see the rocks on the surface, but you really can't see the really defined legible pattern. So come next spring, this is what the surface is going to look like. We're not sure how deep the CO2 frost is, so we don't know how much of the lander is going to be covered up by CO2 frost. Here's that exact same region a little bit later in the spring as more of the CO2 frost has been sublimated away. You can still see remaining water frost in the polygon troughs. And this is the exact same region. So come next spring, this is what Phoenix is going to be facing. Mostly CO2 frost with a little bit of water frost below it. And then it'll slowly start to come out of the frost. And we'll see what actually happens from there. But that's all I have. Thank you for listening. And sorry you missed the debate. Hopefully you can TEGA it or something if you really care.